Hi everybody, my name's Greg. I'm going to tell you about a paper called Restorable Shortest Path Tiebreaking for Edge Faulty Graphs. This is joint work with Marav Parter at Weitzman, and with that, I'll just jump right into it. So thanks for tuning in. So our setup for this talk is going to be, we have a graph G. All graphs in this talk are going to be standard undirected unweighted graphs, and for now we'll use this 5-node toy example. And we imagine that we have run your favorite shortest path algorithm in order to compute its shortest paths. And we'll typically store these in a routing table T. So as a reminder of what the routing table does or how it's structured, the routing table we can think of as a 5x5 matrix, 5 because there are 5 nodes in this graph. And if you want to know what's in a cell, for example, the 1,5th cell, this would be the answer to the question, if you're currently standing at node 1 and you'd like to go to node 5, what should your next hop be? So in this particular case, your next hop would be this green arrow. You would go from 1 to 2, and for that reason, we would write a 2 in this cell. Now, so far, this is very standard, but I want to say that something is going to be different about this talk than other shortest path algorithm talks that you might have seen. And the difference is that we're going to care a lot about tie breaking in this talk. So in particular, let's do this one more time. Let's try to populate the 2,5 cell, basically answering the question, if you're standing at node 2, which hop should you take next to get to 5? And the answer is it doesn't matter. Either of the two options, node 3 or 4, are equally viable and will lead to an equally short path. In many algorithms you might see, they don't really care which choice they make. There will be some tie-breaking rule used on the inside, but it often doesn't really matter, and this is a background detail. For this talk, it's a foreground detail, so I want to prime you right now to pay attention to this. So if you haven't seen this before, a scenario where tie-breaking really matters, you might very reasonably wonder why. What could be a problem or a setting that we might come across where it would be really important to break ties in one way and not another? So let me motivate that for you. And the way that I'm going to do that is by adding a little bit of extra spice to this example that we've started with. So let's say we break our tie in this direction, just arbitrarily for now, go from 2 to 4 instead of 2 to 3. And now let's imagine that edges in our graph can fail, as they often do in distributed communication networks or anything like that. Edges will temporarily go down for maintenance. For the sake of this talk, we're going to imagine that just one edge fails at a time. This will simplify things a little bit. We're also going to assume that the graph stays connected under this edge failure. It's like a 2-connected graph so that no single edge failure can break it into parts. These are just simplifying assumptions. They remove a few technical details that we don't want to have to think about in this talk, but the paper and all the prior work that I mentioned, those don't need these assumptions, just a talk thing. So good, so this fails, and the effect of that is that our routing table is now wrong. Our routing table will occasionally try to tell us that we should be using this edge from 2 to 4 that no longer exists. So in light of that, we need to restore our routing table, and we'd like to do so in some fast, space-efficient, distributed way. In particular, we don't want to be recomputing this routing table from scratch every time a failure occurs. We'd like to do something smarter than that. So this is our motivation, and this is absolutely not the first time that this problem has been studied or discussed. The work on this problem in various settings goes back at least 30 or 40 years, and there's tons and tons of papers on variations of this problem. But I would like to go back 20 PODCs ago to 2001 and tell you about my favorite solution that Afik, Bremler, Bar, Kaplan, Cohen, and Merritt came up with in PODC 01. So the core of their approach was this thing called the restoration lemma. The restoration lemma says that for any failing edge F and any 2 nodes ST, you can always find a replacement shortest path in the post-failure graph that is the concatenation of 2 original shortest paths. So this is a structural lemma that really goes very far beyond this original motivation that we came up with. And indeed, in the years since then, the restoration lemma has been applied in all sorts of settings to fault-tolerant network design, many other problems that maybe have some flavor in common with our setup, but go much further. So it's easy enough to sort of imagine how the restoration lemma might be useful towards computing replacement paths. It's telling you don't have to search over all possible paths, but only this restrictive type of path that is the concatenation of 2 original shortest paths. And that's great. However, there is this one subtle drawback or subtle issue in applying the restoration lemma that I would like to I'd like to make it clear by running through an example. So we're going to use this little simple 4 cycle as our running graph. And let's imagine that this edge fails. This is F in the restoration lemma. So the new replacement ST path is the one that just goes around this cycle in the other direction, from S to U to V to T. So the restoration lemma is promising us that there's some way to decompose this replacement path into 2 original shortest paths. And indeed there is. This works right here. SUV is an original shortest path, and so is the edge TV here. But the catch is that it's not clear that this decomposition plays nicely with tiebreaking. In other words, there are 2 equally short S to V paths, and this decomposition is just sort of hoping that in our tiebreaking, we picked the one that goes SUV, even though we could have just as well picked the one that goes STV. So the restoration lemma is promising you a decomposition into 2 original shortest paths, but not into 2 original tiebroken shortest paths. Similarly, I should point out that there's actually another way that you could decompose this particular path like this. You could do the edge SU and then the triple UVT. This, of course, runs into exactly the same problem. There are 2 equally short UT paths, and you're at the mercy of the tiebreaking, whether or not it actually selected UVT. So there's this tiebreaking issue based on how the tiebreaking goes in the original computation of the routing table. This could cause a problem in trying to apply the restoration lemma. So this Afik et al. Paper does all sorts of very clever algorithmic ideas that it throws into the mix in order to overcome this problem that I'm describing. But on top of that, they also completely anticipated this problem and suggested another way forward. The way forward that they suggested was this open question that we're calling restorable tiebreaking. So they asked, basically, in the design of the initial routing table, is there some way to be clever about the way that we break our shortest path ties so that the restoration lemma works exactly how you would like it to work? So that in particular, this is saying we can choose 1 canonical shortest path per node pair, so that for any nodes ST and failing edge F, we can always find our replacement ST shortest path by concatenating together 2 canonical original shortest paths. This word canonical requiring you to use the tiebroken selected paths. That's what separates it. That's what makes it an open question instead of the restoration lemma, which has already been proved. So good. So this open question is our way forward. We're trying to investigate in this talk whether or not restorable tiebreaking exists. So I'll put it up here and I'll show us this little picture here of what restorable tiebreaking might look like. It's saying, for any 2 nodes ST, we can imagine this dotted line being the true shortest path between them. If an edge on this fails, the tiebreaking is restorable if it guarantees that we can find some midpoint node X such that sticking together pi SX, the selected S to X path, with pi TX, the selected T to X path by the tiebreaking, those 2 things together form a valid ST replacement path. So this is one nice property that tiebreaking schemes might have. Let me mention 2 others quickly. One very simple one that really requires much less introduction than restorability is symmetry. We could define our selection of canonical paths so that for any 2 nodes ST, it chooses the same shortest path from S to T as it does from T to S. This is not strictly required in a routing table. Routing tables have the flexibility to choose different paths. But maybe it stands to reason or intuition, or maybe there's some settings where you would like to enforce this symmetry. So worth talking about. The last one that I'll mention quickly is called consistency. The actual property that is consistency is a bit technical, so I'm not going to say it here. But the important things is that if your tiebreaking is consistent, this guarantees that your selected shortest paths coming out of some given node will form a BFS tree or a shortest path tree. This is not automatically guaranteed by tiebreaking, but a consistent tiebreaking will do this. The other thing that consistency guarantees is that your selected shortest paths can indeed be encoded by this routing table. Not every selection of paths can be phrased as a routing table, but consistent ones can. So this is an important thing to have just to kind of enable the basics of these applications that we're discussing. So good, these 3 tiebreaking properties will be the ones that we discuss: restorability, symmetry, and consistency. And let's see what we've got. So this open question by Affik et al. Can now be phrased more succinctly as, do all graphs allow restorable shortest path tiebreaking? And this question has generally been regarded with pessimism, I think, in the community. People have suspected that there's some graph out there that just won't allow restorable tiebreaking. And there are three reasons for that, I guess. The first reason is this first row of the table. It's that lexicographic tiebreaking, which is a common one that's sort of implicit in BFS search or Dijkstra's algorithm. If you analyze this, it will be consistent on every graph, but it won't generally be symmetric or restorable. There are counterexamples. So this one natural attempt fails. That's a strike one. The second reason why maybe this casts doubt is that there's another natural attempt that also fails. So this is random reweighting. This method of tie breaking is where you take your graph and just add a little bit of noise to all of the edge weights, just in order to break shortest path ties with high probability. And then now they're unique shortest paths post reweighting, and you don't have to worry about tie breaking anymore. So this method of tie breaking, this gets symmetry, and it's also consistent, but it also fails the restorability test. So that's strike two. The second natural attempt failed. And strike three is perhaps the worst of all. There's an impossibility result in this original Affik et al. Paper that says it's not possible to have a tie-breaking algorithm that's generally symmetric and restorable. In fact, looking at this 4-cycle example that we saw a few slides ago, if you really analyze that in a little bit more depth than we did, you can convince yourself that no tie-breaking scheme can be both symmetric and restorable on that 4-cycle in particular. So in other words, no row of this table can possibly check both of these boxes, symmetry and restorability. So having said all that, that's why there was doubt, and you might also disbelieve in this open question if you've forgotten the title of our paper, which is Restorable Shortest Path Tiebreaking for Edge Faulty Graphs. And in fact, that is our main result. We are coming up with a new tie-breaking algorithm that achieves consistency, which is fine. Consistency has been done before, but this check is the important one. It's the first one that achieves restorability. And that's why it's our main result and why we're able to get some applications from it. So good. This is our main result, that all graphs have this consistent restorable tie-breaking. We're using this new algorithm called anti-symmetric random reweighting. That's the name we've given it. So what I'll do next is tell you, what is this algorithm? How are we actually going about the tie-breaking? So here it is. What we do is, our first move is we replace every undirected edge in the graph, UV, with two directed edges, U to V and V to U. Our second move is basically the same reweighting move that I described a moment ago, but with anti-symmetry enforced. So what this is we pick some tiny random variable, calling it RE, that's special for this double edge right here. And we add RE in one direction and we subtract RE in the other direction. For example, here we added 0.000367 in one direction and subtracted 0.000367 in the other direction. So it's just like random reweighting that we described. This anti-symmetric phrase is because we force the same variable with opposite signs to go on these two edges going between the same two nodes, but in other directions. So turns out, if you just sort of smash this with some combinatorics, you can prove that this process is going to give you a directed weighted graph with unique shortest paths. If you take the tie-breaking scheme that just selects the unique shortest paths in this reweighted graph, that tie-breaking scheme turns out it's going to be consistent and restorable. So this is our method. It's honestly not too bad. And the important thing about it, I think, is that it's algorithmic. Really, it doesn't take a whole lot of extra algorithmic work to implement this, or any really real runtime overhead to perform this process. So this is our main result. I'm not actually going to prove our main result. I'm not going to prove restorability. It's not all that enlightening of a proof. Instead, what I want to do is to jump into some applications. So I'm just going to show you basically one application that's emblematic of the rest of them. It's really just a very simple drop-in trick. This really gives you some theorems for low prices by just taking existing ideas and other people's hard work and kind of dropping in this new restorable tie-breaking scheme in the right place. And then suddenly things get simpler or stronger or faster. So to show you this, there's this classic theorem in the area that's called fault-tolerant distance preservers. And what it says is, for any n-node graph in nodes ST, you can find a subgraph that doesn't have too many edges. It only has a linear order n number of edges in it. And the special property that this subgraph has is that under any failing edge, it successfully preserves the distance between the two given nodes ST. So for these two special nodes ST, regardless of which edge fails, G and H are going to agree on the distance between these two nodes. So this has been proved repeatedly and used repeatedly through various algorithms of various complexity levels. What we have as almost an immediate application is really what I think is a very nice, simple, fast construction for this. I think it has some like nice advantages over some of the other approaches. Our entire construction of this subgraph H that I'm describing is we just take our consistent restorable tiebreaking, build a shortest path tree out of S, build a shortest path tree out of T, put those together, that's your subgraph, and that's all, you're done. Just two shortest path trees and you go home. So this is like a very fast, simple construction. The proof of correctness is also pretty easy, it turns out. So the picture of our subgraph looks kind of like this. These arrows represent the tree rooted at S and the tree rooted at T, respectively. This thick bold arrow means that the shortest path from S to T, or a shortest path from S to T, is included in the tree rooted at S. And we can sort of imagine that the edge fault needs to lie along this thick path because otherwise we're done. If the edge fault doesn't lie there, then this path successfully preserves the ST distance. So under this edge fault, now how do we know that this faulted subgraph H that we've drawn successfully preserves the ST distance? Well, this is exactly restorability. What restorability says is that there's some valid replacement path that consists of pi sx to some midpoint node x and pi tx to that same midpoint node x. And since we have included these shortest path trees rooted at S and rooted at T, that exactly means that we've included both of these two parts of the replacement path in our subgraph H. So this is just like a direct application of restorability that basically instantly proves this theorem. So good. So this is our example. I'm going to sort of flash up our other applications that we have here. I won't read all of this to you. We just sort of, improve larger big O things to smaller big O things as one does in a theory paper. The one that I just described is sort of like this second item, source-wise one EFT distance preservers, although we can even handle more than two nodes going on. We also have applications to replacement path algorithms, additive spanners, distance labeling. You can check the paper for more details on these if you're interested, but it's the same flavor of very simple direct applications. The other things we have is, even though we're focusing on one failing edge in this talk, we have even bigger improvements over state of the art for more failing edges, and we have some distributed algorithms that handle all of these problems as well. So there's like my crash course in applications. Definitely check the paper if you're interested in more details on these. I will say that all of these proofs are comparably simple to the one that I just showed you. None of them really require too much overhead. Okay, so there's our applications. I'm going to close out this talk by just mentioning a couple open problems quickly that come out of this. So the first open question I want to point at is a classic graph algorithm is Seidel's algorithm. This tells you that if you get an undirected, unweighted graph, you can compute all pairs shortest paths in matrix multiplication time, and to the omega is whatever time it takes you to multiply two matrices together. It's about 2.373 are the known bounds for this. So this is great, very fast algorithm for all pairs shortest paths, but Seidel's algorithm promises you nothing about the tie breaking. So an interesting open question, I think, is if you can compute one of these consistent restorable tie breaking schemes in the same amount of time, in matrix multiplication time. That would be a very interesting thing to do, and it would speed up some of the applications that we suggested even further. The second is I want to point out that the original motivation that we started with was this story of restoring routing tables after edge failures. Afik et al. Went a lot farther than we did in terms of showing experiments. They really showed that their method was experimentally effective, but they were paying this overhead in their method related to the fact that they didn't have restorable tie breaking at their disposal. So we definitely have like theoretical speedups over Afik et al., but sort of checking this experimentally or seeing how serious these speedups are on practical graph topologies, I think is a fairly interesting direction as well. So great, thanks for your attention. I'll stop there. One thing I'll say quickly is if you have questions on this, either find me at the conference. I would love to talk to you then, or in the meantime, feel free to send me an email, bodwin@umich.edu. So thanks so much for your attention and take care. I hope to see you at PODC.